postdoctoral fellow at the University of Sherbrooke with the Quantum Institute. So today I'm going to tell you a little bit about the work that I've done here, and you can see the title. It's called Phonon Magnetochiral Effect of Pan-Geometric Origin in Weyl Semimetals. Now, this work basically got published in Physical Review Letters quite recently, and it's a result of a very fruitful collaboration with the two people you see on the screen. So the first one is Nabil, who's basically who was an undergraduate intern when he joined the project and is currently a first-year master's student. And our group leader, who's Professor Jon Garrity. So it's basically Dr. Garrett's vision that me and Nabil sort of worked very hard to accomplish. So for these purposes of the talk, there's a lot of ground to cover. And I'm just going to concentrate on the physics of what's the phonon magnetochiral effect and how do we find it in Weyl semimetals and what's basically the physical reason behind its appearance. And I'll share with you the methodology or the formalism that we use to find this effect. And there will be a lot of details and technicalities which I'm not going to share or delve into much. But if you are interested, I would invite you to certainly look into our paper. So I will begin with what's the definition of the phonon magnetochiral effect. So here you can imagine that you have a sound wave. Let me start my pointer. And this is given by a wiggly line and labeled by a vector q. And suppose you are applying a magnetic field given by this arrow, and it's B. And I ask you, let's measure the velocity of sound within the application of the magnetic field, and you tell me it's CS. So now I tell you, let's consider another configuration where we have this sound wave still in the same direction, but we flip the magnetic field. So the magnetic field is no longer parallel, but antiparallel to the propagation of the sound. And I say, let's measure this velocity. So suppose this velocity is called CS prime. So what the phonon magnetochiral effect tells is that this CS is not going to be equal to the CS prime. And the definition of this effect would be sound velocity differs for parallel and antiparallel propagation with respect to the external magnetic field. Now, this I'm discussing in terms of phonon, but this actually happens in case of most of the quasi-particles or excitations. So it happens for photons, electrons, magnons, and as I said, for phonons too. And it's a very fundamental effect. Now, we all do know what photons are. It's the quantum of excitation of light. I don't need to define electron. Magnons are spin wave excitations, and phonons are basically the quanta of excitation of lattice vibrations. And for the purposes of these talks, what I'm going to do is to tell you about acoustic phonons. Now, the phonons which are responsible for propagation of sound and heat. And we are going to concentrate only on sound. Now, although the photons and electrons and magnons, this effect of magnetochiral, is easy to experimentally sort of observe, it's not certainly very easy to observe for the phonons. And that's because phonons don't necessarily or easily couple with magnetic fields. So you have to do something for the phonons to sort of couple with the magnetic field. And up until recently, there was no sort of experimental proof whether this phonon magnetochiral effect can be observed or not. Until last year, in 2019, there came a first experimental proof. And you can see that this is a paper that came out in Physical Review Letters in 2019. It was also the editor's suggestion, and it was featured in Physics. And what they tried to show, and this is an experimental paper, they basically showed that if you pass ultrasound through a chiral ferrimagnet, which is a copper oxoselenide, you will see that the velocity of sound will flip with the magnetic field orientation change. And theoretically, they explained this as sort of a hybridization that happens between the magnons of the chiral ferrimagnet and the acoustic phonons. So what they are predicting is if you have a chiral quasi-particle like a magnon, it can couple with the phonon and render some of its chirality to the phonon. And then this phonon can, propagate or change its direction with the direction of the magnetic field. So we sort of read this paper, got very interested, and we decided to do something about it. So here's what we would like to propose, and here's what I would also cover in this talk. So my first question would be, are there any other materials that exhibit this phonon magnetochiral effect? So for this talk, I would just refer it to as PMC. So anytime you hear PMC, know that it's the phonon magnetochiral effect. And if yes, there are materials that can exhibit this PMC, can we build or gain a theoretical understanding of it? So with that, let me begin by showing you our choice of material. So most of you may have seen this sort of cones where these are just the linear dispersion equations for electron. And if these two nodes were at the same point, it would be a simple Weyl semimetal with the Weyl nodes here. But this is a special Weyl semimetal. It's called a chiral Weyl semimetal because the Weyl nodes are actually at two different energies. Now, for a normal Weyl semimetal, these 2 points are at the same Fermi energy, but for a chiral Weyl semimetal, these 2 points are at different energies. Now, this is a toy model, but there are candidate materials where this appears, and they are called cobalt silicide and rhodium silicide. Now, to give you an idea of this material, I would say that these nodes are characterized by different Fermi velocity, different Fermi energy. They're also characterized by large Berry curvature and orbital magnetic moments. And for the purposes of this talk, I would just, write the Berry curvature as omega p, proportional to c, which is the Chern number. So there are other factors too, but whenever you see in an equation you have a modulus of c, know that it comes from the Berry curvature. So I'll just keep the equations very condensed and keep this as proportional. So now that I've told you what materials or what material we are going to probe this phonon magnetochiral effect, let me show you what's the methodology. Also, please let me know if I'm going very fast. I'll just slow down a little bit. So the methodology here is, as I told you, the phonon doesn't couple directly to the magnetic field. So we need to do something. So what we need to do are two things. The first one is couple the chiral electron in the Weyl semimetal with the acoustic phonons. What this is going to do is it will make the electron transfer or sort of give its chirality to the acoustic phonons. And how it will do that, I'll tell you in a bit. And the next point would be that when you have this chiral acoustic phonons, just study or investigate its dispersion. And once you have the dispersion equation, one can readily figure out what is the velocity or the attenuation of the sound wave. So I'll tell you how to do that. So let's begin with the first step, which is to couple the chiral electron with the acoustic phonons. So the formalism that we take is basically sort of devised by Landau and his students starting from year 1938. But of course, they didn't study it for topological materials. They studied it for topologically trivial systems. So what this method tells us is the following. Suppose you have here a slab of chiral Weyl semimetal, and the sort of gray dots you see are the atoms there. And the red arrow here gives you the direction of a constant magnetic field that you apply to the geometry. And I say, if this video works, yeah, it does. So I say that let's put an ultrasound wave through this semimetal. And what it does is, as soon as you pass this ultrasound wave, these atoms, they start to jiggle. And when this atom starts to jiggle, these are basically the phonons, they cause the electron in this Weyl semimetal to move a bit. And so what happens is that this electron, which is a chiral fermion in this material, interacts with this phonon and its energy gets deviated. So in order to figure out how this chiral electron would make the phonon or give the phonon some of its chirality, we have to understand how this electron phonon coupling happens in this material. And there's a way to do it. It's called the Boltzmann kinetic equation. So what I mean by this is, when you pass the sound through this material, it drives the electron out of equilibrium. And to understand this problem, what we have to do is to apply Boltzmann kinetic equation. And let me give you the formula for it. So here, F stands for the Fermi-Dirac distribution that explains the electron. And each of these terms on the left-hand side, the first one is how the distribution of electron changes with respect to time. The second one tells you how the distribution would change with respect to space. And the third one tells you how the distribution of electron would change with respect to momentum. And the term on the right-hand side is a special one. It's called the collision integral. So it tells you how the electron distribution would relax finally from this out of equilibrium position to this equilibrium. And this happens by virtue of some relaxation time. So in order to know how this electron-phonon interaction happens, what one has to do is to understand how this Fermi-Dirac, or this total electron distribution appears in this Boltzmann kinetic equation. So one thing you can see is, to solve this equation, we have to know what these R dots and P dots are. And these are nothing but the equations of motion in a magnetic field. So here I have for you the equations of motion of the electron. So this R dot gives you the velocity, and this P dot tells you about what's the force on this electron. And this is written in semi-classical formalism. So because this electron is in a topological system, so you have in the velocity, the first term, which I'll explain to you what it is a derivative of this energy. And the second term is the anomalous velocity, where this omega p is the Berry curvature. And this force here is defined as a sum of three terms. The first one, where you see the capital E, is basically the electric field that is resulted because of this electron-phonon interaction and the lattice vibrations. So this is an electric field associated with the phonons. This is just Lorentz force. And this one again is a derivative of an energy term. So let me define to you what this epsilon P is. So this epsilon P is basically the deviation in energy of the electron due to the phonon, or the phonon electron-phonon interaction. So here is the bare energy of the electron, and here is the term that tells you how the electron-phonon interaction changes the energy. And this functional U is basically the position or the jiggles. So the phonon can be in any coordinate, x, y, z, so 1, 2, 3. So once you have the electron's equation of motion written in terms of the electron-phonon deviation, in terms of the displacement of the phonon, what you do is to just plug it back to the Boltzmann kinetic equation in these terms. And then to know about how the electron may have changed due to this electron-phonon interaction, what you need to do is to just solve this Boltzmann equation to get this total electronic distribution. So we'll do that, and then we have to go to the second part of the methodology. So the first part, where we do what I told you before, sort of gives us how the electron couples with the acoustic phonon via the electron-phonon interaction. And when we solve that, we get all the knowledge about how the electronic distribution function is in terms of magnetic field, in terms of Berry curvature, in terms of electron-phonon interaction. Now that we know all of this, what we need to do is to find out how this gets into the phononic picture. So that would be to solve or to understand the dispersion of the acoustic phonon. And how do we do that? Well, for doing that, we need to have the elasticity equation for the lattice. So this is just standard, Hooke's law. You can call it the Newton's second law. And this first term here on the LHS, this is the density of the material. For most purposes, this is known. This term ui double dot is actually a double time derivative of the displacement of the phonon. And this term here is the elastic moduli. And this is written when you don't have any conduction electrons in your system. However, if you have conduction electrons in your system, and you make it to interact with the phonons, then there will be a force that this electron-phonon interaction will cause. And this will cause the conduction electrons to deviate or drag a bit. And this is called the drag force. And as you can see, that this drag force is basically a solution of the Boltzmann equation. So this is how these two equations are coupled. One has to first understand everything about the electronic distribution as a function of electron-phonon interaction. Once one has understood it, one has to plug it back to the elasticity equation, taking in consideration that there is an extra force on the conduction electrons because of this electron-phonon interaction. So this equation out here is basically an eigenvalue equation. And if one writes it in the Fourier space and tries to solve it, one will get the eigenvectors and the eigenvalues. And each of these eigenvectors are basically the modes of the phonon vibration, and the eigenvalues will be corresponding energies corresponding to the modes. So here, let me tell you about how this dispersion of phonon looks. So if you solve that eigenvalue equation in the previous slide that I showed you, for zero magnetic field and no electron-phonon interaction, you will get a dispersion that looks something like this. And this is standard. Most of us may have seen it. So here, omega is the eigenenergy or eigenvalue, and Cs as a function of zero is basically telling you what's the velocity of the acoustic wave when the magnetic field is zero. And Qz here is the phonon wave vector. And when the sound passes through a certain length of a sample with a certain depth, it obviously decays, or it attenuates, and the imaginary part gives the attenuation at zero magnetic field. But our problem here is to figure out what happens when we have this deviation due to electron-phonon interaction, or when we have this magnetic field presence. So what happens in that case is we have two additional terms, and these are correction terms that are given by a real part. And this real part basically tells you how the velocity of the sound changes in presence of electron-phonon interaction and magnetic field. And the imaginary part here tells you how the attenuation would change in presence of electron-phonon interaction and magnetic field. So once you have this equation, what you need to do is to calculate the velocity and the factor that the experimentalists would finally measure in the lab, which is called the VMC. So I'll explain to you what these are. So the velocity is generally derived as a derivative of this correction with respect to the phonon wave vector. And the factor that experimentalists would finally measure is for the phonon magnetochiral effect in the velocity is defined as the following. So
I'm
here,
sorry, Sanghita, if I might say a word. So the velocity, I guess it should be the derivative of omega with respect to QZ, not just delta omega. Velocity,
yeah, I see what you're saying.
Okay, yeah.
So what Dr. Garrett said is it would have both the zero magnetic field terms and the linear in magnetic field terms. But if you want to, that's right? That's what you're trying to say?
Yes, so instead of taking the derivative of delta omega r with respect to QZ, it should be the derivative of the full omega, the one you wrote above, with
this
respect
one.
to QZ.
Yeah. So if I may continue, so what the experimentalists in ultrasound experiment would measure is this VMC, and that's basically the velocity as a function of the phonon wave vector and the magnetic field, minus the velocity as a function of the phonon wave vector and the reverse of the magnetic field. And it will be ratioed by the velocity as a function of no magnetic field, like zero magnetic field. So this is what experimentalists would basically measure in the lab in terms of the velocity. Now, if you want to measure the attenuation, what you have to do is consider you have a sample of size L with the velocity Cs, and this is the attenuation factor. And if you want to be specific, it's this plus this term. And then you just consider that this is the phonon magnetochiral effect in the attenuation. It's given by just this factor at QZ and BZ minus this factor at reversed BZ. So Q remains the same, but we just flip the direction of the magnetic field. Once again, ratioed by the attenuation when no magnetic field is present. So this is so far the methodology. And if you plug in all the solution of the total electronic distribution in presence of electron-phonon interaction from the Boltzmann kinetic equation, plug it back to the eigenvalue equation for the elasticity into this VMCs and RMCs, what you're going to get are these results. So this result that I'm going to show you here is just for a longitudinal phonon mode. But if you're interested, you can look for the other phonon modes, which are in our paper. So what I mean by the longitudinal phonon mode is the following, that the phonon is basically traveling parallel to the displacement of the phonon. So the vectors are parallel to each other in that case. So in case of the longitudinal phonon mode, if you calculate the VMCs, and here I'm just writing it in terms of proportionality to give you like the terms that are physically important. These are very long equations. So the first thing you note in case of the velocity is the following. So this is proportional to modulus of C, which I have defined before as the Chern number. And I've also told you that whenever you see this modulus of C, you have to remind yourself that this appears because of the Berry curvature or the orbital magnetic moments. So this VMC in case of the chiral Weyl semimetal is the origin of this term is the Berry curvature or the orbital magnetic moment. The second thing to note is you have an odd factor of BZQZ. So BZ here is the constant magnetic field that we have applied, say in the direction C. QZ is the phonon wave vector. So this always appears together. And there is also an absolute value, which represents the sign of the phonon wave vector. And there is this factor called delta lambda. And this delta lambda is basically it captures the electron-phonon interaction or the pseudoscalar deformation potential, which defines the electron-phonon interaction or the magnitude of it. And there's also this factor gamma E. So this gamma E I haven't defined yet before. So if you consider that there is longitudinal phonons in your system, so from mathematical derivations, what we found is these longitudinal phonons, when they travel parallel to the magnetic field, they create a charge imbalance. So concentrate on this figure here, and this is just for schematics. You have two chiral Weyl nodes for the chiral Weyl semimetal. Here's node 1 and here's node 2. So when you have this longitudinal phonon, they will create a situation where the charge is not balanced between this node and this node. So there will be an valley imbalance of this charge. And in case of Weyl semimetals, whenever there is a valley imbalance or valley charge imbalance, it's called chiral anomaly. And this non-equilibrium distribution then has to be sort of relaxed. And how it gets relaxed is by this scattering rate, which is defined as inter-valley scattering rate gamma E. And you can also see here that I have another factor called gamma A, and this is the intra-valley. So there may be charge imbalances within the valley, and that will relax through this gamma A. So in case of Weyl semimetals, typically this gamma E is much smaller than gamma A. And so when this gamma E appears in our equations as a small quantity in the denominator, this VMC becomes quite enlarged. So similarly for RMC, you can see that this is the attenuation part. You have the result, which is proportional to C, which is the Berry curvature. Once again, it is proportional to odd in B and odd in Q. And it also depends on the electron-phonon interaction or the deformation potential. And it also scales as gamma E. So the results here, they tell us that the PMCE, or the phonon magnetochiral effect in these Weyl semimetals, are driven by Berry curvature. They are odd in momentum of the phonon vector as well as the magnetic field. They're proportional to the deformation potential or the electron-phonon coupling, and they're inversely proportional to the inter-valley scattering rate. which is related to the chiral anomaly in these materials. So if this result an experimentalist would want to sort of probe in the lab, what they would have to do is to use ultrasounds. So here's a plot that has on the y-axis the VMC, and on the another side of the y-axis, the RMC. So this tells you about how the velocity changes. This tells you about how the attenuation changes for the phonon magnetochiral effect. And on the x-axis, you have the frequency. So it goes from 0 to 1000 megahertz. And you can see that this black line here corresponds to the velocity change. And the red line here corresponds to the attenuation. And here I've written a factor 10 to the power 6 because the resolution of ultrasound detection for velocity is around 10 to the power minus 6. And here I've written a factor 10 to the power 2 because the resolution of the ultrasound is around 10 to the power minus 2. So you can see that as you increase the frequency, as it increases and much beyond 500 megahertz, this velocity is sort of detectable. So it is within the resolution of what the ultrasound can measure. Similarly for RMC, the attenuation, you can very much see the same, that if you increase the frequency, this RMC is very much detectable within the resolution. So I believe I have to sort of come to the end of my talk. And so I'll just quickly give you the conclusion. And so what we have done is basically probe the phonon magnetochiral effect in chiral Weyl semimetals. And as I told you, that the chiral Weyl semimetals belong to this group of cobalt silicide and rhodium silicide. In this case, the sound velocity basically differs from parallel and antiparallel propagation. So if you have a magnetic field and the sound velocity, if you flip the orientation of the magnetic field, the velocities are not going to be equal. The attenuations are not going to be equal. So this is the phonon magnetochiral effect. In terms of chiral Weyl semimetals, the origin of this phonon magnetochiral effect is driven by a few things that I would just summarize. The first is the electron, which is the chiral electron in case of chiral Weyl semimetal, sort of transfers its chirality to the acoustic phonons via an electron-phonon interaction. This entire phenomena in this case of chiral Weyl semimetal is driven by a Verret curvature, or the Chern numbers. If in case it was a topologically trivial material, we would not have seen it in this case. The other important thing is when you have longitudinal phonons, that is, if the phonons propagate collinearly with the magnetic field, you will see that these phonons create a charge imbalance between the two values. And this charge imbalance is nothing but the chiral anomaly. And this charge imbalance is then relaxed via an intervalley relaxation rate. And because this is low, this intervalley relaxation rate for the Weyl semimetals, this effect of PMCE is basically visible. So certainly there are many details and technicalities as well as motivation for this project that I have not told or covered in this 20-minute talk. But if you're interested, I invite you to take a look at our paper. And if you have questions, I would take them and try to answer them. So thank you all for your attention, and I wish you all a very good health. Thanks a lot. I'm ready for any questions if you have any.
Thank you very much, Sanghita.
Should I close this, stop broadcasting this?
You can stay if there are questions about your presentation. It would be better if you can answer them using the PowerPoint. No questions? Well,
yes,
so let's.
I raised my hand.
Oh, sorry.
Thank
you
you,
just go ahead.
Sanghita, for this very nice talk. Just one quick question. I didn't see the energy difference between the two valleys. Where does it come from? Where is it in the formula?
Oh, you mean in the VMC and the RMCs?
Yes, I mean, you see the two nodes are not at the same energy. Is it important?
It is important because in this formalism, you have the density of states that actually appear. So I haven't written the full formula here. Maybe I can write it now. So in this VMC, you also have terms that appear as, can you see? 1 plus 0 minus 1 minus 0 divided by 1 plus 0. So this is basically the density of states around each node, this one. So in order for having the density of states, this actually scales as the Fermi energies. So this is where the energies of each of the nodes, as well as the Fermi velocity enters.
Okay, thank you very much.
So if I may add one more thing, is that you see, André-Marie, that delta lambda there. So that is really the difference in the electron in the deformation potential between one node and the other one. So if the two nodes were related by asymmetry, then they would have the same energy, and also you would expect that the deformation potential would have the same intensity in the two nodes. But once you break the symmetry that relates those two nodes, in this case it will be a mirror symmetry, then as Sanghita said, density of states need not be the same at the Fermi level, but also the deformation potential need not have the same value at the two nodes, and that is also important for this effect. Yeah.
Yeah.
Okay, thank you very much.
So Michel, you can go ahead and ask your question.
Yeah, thank you for your presentation. But you, what I want to understand is that you're describing a method to account for this the phonon, this magneto effect in chirality in phonon in the presence of a metal, and a wild metal, because there was some experiments at diaphragm groups on insulators. This will not help to explain these results.
If you're talking about the recent paper, I think it is on tantalum arsenide, right? So that is a little different from this model that we are talking about.
No, actually, Sanghita, I think maybe Michel is referring to the thermal Hall effect in Mott insulator.
Yes.
Oh,
Yeah.
okay. I didn't know about that.
Yeah, that's indeed. They also have a paper on Louis and Jeff Quilliam. They have a paper also on the ultrasound in tantalum arsenide, but that is not, I think, what you were referring to. Yeah.
No, but
yeah,
I'm interested in both.
so that's an open question, and I think
Okay.
if you can, yeah. So of course, they also use the word chiral phonons, but I don't think it's really the same sense. So one question is that in this case, we didn't calculate any phonon Verret curvature or so on. Would phonons coupled to chiral Weyl fermions also acquire some Verret curvature? And if they did, then they would also lead to the thermal Hall effect in the same way as. But of course, here you would also have. Because this is a semi-metal, you would have electronic contribution as well,
Right.
Not
Okay.
just phononic. But that's one question that I think I don't, at least personally, I don't fully understand. Is the chirality that Louis talks about related to the chirality that we talk about here? So yeah.
Okay. Thank you.
Yeah.
So if there are no more questions, thank you again, Sanghita, for this very nice talk.
Thank you.
And
Stop the broadcasting.
yes, you can. Great. So now we are going to a second seminar from Simon Verret, which was a PhD student in Sherbrooke, who now is a doctor in physics. He's working as a postdoc between Sherbrooke and Montreal. And today he's going to talk to us about analytical continuation, this very difficult problem, as he will tell us. You can go ahead, Simon.
Hi, Nicolas. Can you allow me to share my screen? I cannot share it right now. Aha.
You can share it now.
Perfect. It works. This one.
Thank you.
Sure.
Would you prefer questions during or after your talk?
You can interrupt me whenever you want to ask questions. I will try to do it fast. My slides extend for a long time, so maybe I will stop like right in the middle of my talk, but I don't really mind that. So I have a talk which is in 3 parts, and I hope I will get to the end of the second part. but the results and the interesting project is all in the last part. So maybe we won't get there. So sorry about that. So, okay, so basically this is work. I will keep it very introductory. I want to give you intuitions about the problem we were trying to solve. We will go into kernels, condition numbers, and at the end, the work we did is on temperature invariance. Maybe we won't have time to talk about this. This is work done with Reza Nourafkhan, who you probably know was at IQ for a long time. Samuel Desrosiers, a student in Sherbrooke. Quinton Weyrich is an intern that we had this summer from Waterloo. And this is work done, enabled by Yoshua Bengio and supervised mainly by André-Marie Tremblay. I worked at Institut Quantique and Mila, thanks to a scholarship given by Ivado. So if you are interested to do that kind of collaboration, they have a program for postdoctoral scholarships and PhD also. And if you read the fine print, there is a part where you can do like partnerships between institutions. So that's how we did that. And I had a very good time at Mila, and it's getting to an end. So this project is almost over for me, but it's not finished. There are a lot of things to do. If you are interested by this project, keep in mind that you could decide to pursue it. I will be here until Christmas, and I could like have a chat with you to explain what you could do or what would be the next steps. If this is something you want to take on, I would be very happy with that. Okay, so my first part, so each part of the talk, there are three. There will be a big slide like this. So the first part is very easy. I want to show you that you can go from your pocket to analytic continuation. So basically what I mean by that is that right now in your pocket, you probably have a smartphone, or maybe it's on the table or whatever, but many times we have smartphones in our pocket now, and never in the history of humankind have people carried with them so many elements of the periodic table as you can see there. So what I want to say with this is simply materials are an important part of the technology. And we all know that, right? It's the quantum material seminar after all. So quantum materials in particular might be in the future one of the bedrock for very sci-fi technologies. We just heard about magnetochiral effects on caloric effects, and if you think about graphene, you have many properties, superconductors and their magnetic field expulsions, topological insulators. Those are examples of materials in which we see very great promise to build new technologies, but since we don't understand all the way it functions very well, we cannot do engineering of those materials. Okay, and this is mainly because like one of the main reasons for this is electron correlations, because as you know, usually in materials, in crystalline materials, you expect to have like very neat Fermi surfaces, but if you go into correlated materials like the high temperature superconductors, those Fermi surfaces can disappear. You see very exotic behavior there. The reasons for this are not all understood. And another example of this is if you looked, for example, at the optical conductivity of a material, if a material reflects light correctly or absorbs it, or does it have a great electrical conductivity at given frequencies, as a function of frequency, you can change that in a strongly correlated material just by changing the number of electrons. Now, I don't know if there are any like real applications for this that are done in the labs, but if you think about it, you could say, yeah, maybe you could create a material which is a mirror at a given at a given tension, and change the tension, change the number of carriers in the material, and then make it transparent or something like this. So these are the kind of applications we're talking about if we were able to engineer how this conductivity moves as a function of given parameters. So this is one example of what we could probably do with strongly correlated materials. And as we all know in this seminar, probably like the problem with these materials, the reason why we cannot compute their properties properly is because although we know all the physical laws necessary for a large part of physics and the whole of chemistry, let me just annotate like this. Yes. Now you see something on my screen, do you?
Yes.
Yes, perfect. Okay, so the whole of chemistry, completely known. This is a citation by Paul Dirac, which is often used in introduction to talks like this. And the main thing in here is that it becomes desirable to find approximate practical methods of applying those physical laws in the real world. And now we're 90 years after that quote. So if we fast forward 90 years, one of the state-of-the-art method to do that is what is called quantum Monte-Carlo. And quantum Monte-Carlo nowadays, if you're familiar with it, you know that it's combined with other methods. It is often used as one part of a larger scope of methods. And it enables very powerful calculations. And one of the key reasons why it enables calculations is that often we do quantum Monte-Carlo in imaginary time. Now, imaginary time is simply a mathematical trick that we use to unify the time evolution in a quantum Hamiltonian with the temperature dependence. And this is done just by noticing that both those terms are exponentials of omega because of quantum mechanics, and then the imaginary time and the temperature looks kind of the same. And this enables to go to a space where the problems become simple. And how simple, you could say, well, if you think back about conductivity again. So if you have a system for which the answer, like the conductivity that you would compute if you were able to compute everything looks like this is a synthetic example. Then if you look at the corresponding quantity, so this is the conductivity as a function of frequency, the corresponding quantity in the imaginary time domain would be the response function as a function of the Matsubara frequencies, which are the frequencies on the imaginary axis. And the corresponding function for this one is very smooth and goes like this. So you see that in imaginary time, usually functions are more simple and hence are easier to get with various Monte Carlo methods. Now there are a lot of like details that I don't have to go into right now about this, but basically that's why it's easier to work with these imaginary frequencies. So the link between those two at the end of the day, because what you want is the real-time conductivity, the link between those two is given by a formula like this, okay? So on one side, you have the real part of the conductivity, which is exactly what you want here. And then you have this kernel, and then you integrate the conductivity and you get this response function. So as you can see, going from here, the one that you get in Monte Carlo to here, requires to invert an integral equation. Now this looks complicated, but you can think of it simplified if you say, okay, we'll get a given set of samples for this function, which are those points that you get anyway from a finite temperature analysis, and we'll try to obtain a given sample, a given vector of samples of this function here, there. And then you can see the kernel as a matrix multiplication, and it's not so hard anymore. What you have to do is to invert a matrix. So
I'm sorry, can I ask a question?
Yes.
So that plot of conductivity that you showed, I'm just curious, does it correspond to what kind of model is that? Is that, or is it some random choice?
Yeah, very good question. So this is completely synthetic. Okay, I wanted to have a peak at the middle because that's often what you see in materials that have one band crossing the Fermi level. You have a peak for the band crossing the Fermi level at the energy of the Fermi level, and this is the Drude peak, which corresponds to DC conductivity. And then at finite frequency, you will have transitions that are allowed only if you have like gaps at that particular wave vector. So that's why we showed it like this. The peak is a little bit too large for being physical. The humps here doesn't mean anything. We just wanted like a good shape. And you will see why at the end, because we were trying to train neural networks to do that task of inverting the integral. And we wanted to like generate many spectra like this or conductivities like this, compute what they would give in imaginary time to train the neural network. So we needed like synthetic examples like this.
Okay, thank you.
Okay, and okay. So as I said, you can see the problem as an inverting a simple matrix. So why is it so hard? Well, there are problems where the setup is simple, but the answer becomes impossible to get. So for example, here I will give you an intuition about why such a problem can be so difficult by discussing a very basic ill-conditioned problem. And we will start by showing you an impossible problem. And this is a basic impossible problem. Given a number y, which I say is the sum of 5 other numbers, try to find the 5 other numbers. So obviously this is impossible. It's trying to invert a single sum. However, you can make this problem possible if I say, given a collection of numbers y and a collection of equations corresponding to those numbers, given the same input, try to find the input. And now the matrix, this matrix, which contains almost exactly the sum of all the x on each line, but weighted a little bit higher on one of those numbers for each line and a different one for each line, then you get a problem which is solvable. And then something interesting happens. Like if you take a very small number for epsilon, okay, so I give you y1 as the sum of all the x's, and I weight x1 a little bit more on this number. And then I do the same thing for y2, but I weight the x2 a little bit more for y2 and so on. Then you get almost identical numbers as an input. And if I ask you to solve for x, to find the x, what you have to do is basic. You have to inverse the matrix and you will get the solution. Okay, so the real solution is the pink one in behind. And if I work with this inverse matrix, I will get the red here. And now I will do the simple exercise of saying, if I add a little bit of noise to the inputs of this problem, then I will play exactly where the data is contained in the small differences that are in the y's. And if I try to find a solution again with the exact inverse of my problem, it will be unstable. And the same thing happens at various levels of noises. And you can see that at a given number of noise, I will have like very, very large uncertainties about what was the truth. And this is an exact computation, right? So I have an input which has a small amount of noise. I pass it through an exact inverse for my problem, and I get very, very wrong answers. This is what is called an ill-conditioned problem, a problem where you cannot get the answer unless you have infinite precision or almost infinite precisions on the input. Okay, so I want to ask you a question regarding this. So I thought I would be able to get the chat, but I cannot see. This is annoying. I would like to see who is raising their hands and so on, but I cannot. Okay. So we will do the question basically in your mind. So if I ask you, given an error input, so that's it. That's what I mean by that, an error in y. Okay. What will be the error at the output? So if I increase the error in y, like I was doing in that slide, I was increasing the error in y. What will happen to the error in x, the answer that I'm looking for? Will it grow linearly with the error in y? Will it hit a threshold b where it becomes very high, or will it grow exponentially? So, because this is a good question to ask about ill-conditioned problem in general. And the answer to that question is that it will be linear. And the reason why it is linear is simple. You multiply the input by a matrix, which is A inverse. And if you do that, you will always get a linear outcome given the input. So you can compute the condition number. In the case of the matrix like that, it's the norm of the matrix inverse times the norm of the matrix. And the condition number will give you an idea of given an error in the input of the problem, what will be the error on the output of the problem? And you can see that in this case, the growth of the error is drastic. You have like a factor of more than 1,000 given the error in. This is something very standard. It's called the condition number. You can look it up on the internet. And for this particular problem, where I had this matrix with small variation of epsilon, the error will be the condition number, which is basically simply a characteristic of the problem itself, not of the data that you're treating. So the matrix itself has a condition number. It tells you how much it grows the error in. And if you change the value of epsilon inside that matrix, you will find that the error is inversely proportional to the condition number. So the error amplification is inversely proportional to this epsilon number. And this error amplification will hit very high number, to 10 to the 5 and 10 to the 7 when the epsilon number is very low. And when you get an epsilon which is 0, which would be like having the sum of your inputs at every rows of your matrix, then you cannot solve the problem because you only have 5 times the same number to work with. And then you have an infinite condition number. So condition number infinity equals an impossible problem. And in the analytic continuation, the condition number is of the order 10 to the 14th from what I've computed. Now, I'm not sure that my computations of this were exact because you hit some of the limits of the computers at some point, but it's simply to say, yeah, analytic continuation is very, very hard. The solution exists exactly if you take a finite matrix for the problem, but it is so sensitive to noise that if you don't have the exact right input, you will get a completely different output for the analytic continuation. So given those values, if I'm asking to find the right spectra, but I have noise on those values, I won't be able to find the right spectra just by inverting this kernel, okay? And you can see why if you look at the kernel of this analytic continuum problem. So here I will plot A. So this is the kernel. And for the first point that you get here, you have to multiply that function with the kernel and integrate the result. So in that case, it's 1 everywhere. So you integrate the function here, you get that value. And then you integrate the function, but you weight the middle peak differently, and you will get the second value, and so on. And you can see that the structure of that peak is entirely encoded in the difference between those two values. So you can see that because of the finite samples that I have here and all the details that would be between those two samples, if I had worked with the continuous omega n, still the structure of small features at low frequency are contained in very, very subtle changes in the Matsubara, in the imaginary time information. And this is why analytic continuation is so hard. Okay, so we have 3 minutes left. Nicola, maybe you can tell me what we will do. I suggest that we take a break, people can leave, and if people are interested to continue, we can go on to the neural network part, but otherwise I will take questions and we can stop here if you prefer. It's like you want.
I mean, yes, this is actually a great idea. People want to take the time to listen to you further. So, does anyone have questions so far? I'll check that. No, I guess there are no questions now.
All right. So is it okay if we call it a day for most people? And I will be back in 2 minutes for those who want to continue to hear about the neural networks part of this talk.
That's fine by me.
That's fine. Okay, so thank you very much for the first 2 parts. And if you want to hear more, I'll be there for another 20 minutes, so not more than this.
See you.
Okay. So I guess if you stayed, that's because you want to hear more. So that's good. Thank you very much for being there. Okay, so now about neural networks. So the idea is that for a hard problem like this, you could say, let's build like 100,000 examples that we know work, like input-output pairs, and let's train a neural network and see if it does well on other examples. So to do this, what we can do simply is to generate random functions for the conductivity to compute what they will get for pi. And you need to compute it with a high precision because, as I said, small amount of errors here can cause a large error in the result. So you prepare a very tightly computed data set, and then you can train the neural network given this pi input as a vector, like, and we use 128 components for that function, so 128 Matsubara frequencies. Train the network to produce the right samples for sigma. It is not the only way to do that. You could have thought like to use the neural network with an input for omega and try to produce a single output, which would be the value of the function sigma at omega or other things like this. And you could use more sophisticated architecture than a simple neural network. But we wanted to work with the simple neural network because other people in the literature had worked this way, and we wanted to see if we could improve those methods directly. So we have always neural networks of 128 to 512, and basically the architecture ended up being 2,000 neurons width with 3 to 4 layers of depth. And usually this works pretty well. So the results you get when you do this is the input pi, and you get the conductivity like this with the target, the exact target here, and the result for a neural network shown in red. So you can see that for this case, it's very good. And then the neural network will have some examples which are harder. And for example, this one, it doesn't fit pretty well on the data. So for each of those spectrum that you insert and get the, for each of those pi that you get the sigma, you can compute the error and see how well the neural network does for 10,000 examples, for example, for instance. So what we started to do was to say, okay, this is right. We can do this if we work at a single temperature, that is with a single grid of Matsubara frequencies, and with given scales, like a given grid for real frequencies. But would it be possible to generalize and work at many temperatures with the same neural network, or to work on various frequency grids for the same neural network, given that all the neural network takes as an input is a vector pi without information about what was the grid on which it was sampled, and the only output it produces a vector of values for sigma without information about the grid on which those values were produced. So since the neural network is itself agnostic to the grids we use in frequencies, could we do the same with the data and produce data that would be agnostic to those grids? So this is the work we've been doing, and it was submitted and accepted recently for a workshop at the NeurIPS conference that will be held in 3 weeks. And basically the way we did this is the following. So we wrote carefully the equations that we were trying to invert. And if you write it with pi expressed as a functional of the function that is going into the integral, and as an explicit function of the temperature, which enters the Matsubara frequencies definition, well, what you get is that there is an invariance in this integral because you can do a change of variable and like isolate the scale or a linear scale S that you change the variable, the omega with, and put it right into the Matsubara frequencies. And in that way, what you will find is that you can see it in 2 ways, which we found are useful to think about that. The first way is to say the components obtained at a given scale of Matsubarra frequencies, which is exactly what the temperature is. So the components obtained at a given temperature are exactly the same as rescale component for another function of this omega n. Or another way I like to think about it is the components of this that we're trying to produce. No, the components that we will get as an input for a given function at a given temperature are the same as the components given as an input for another function at another temperature. So if we try to make the problem agnostic to temperature, we have to bind that to the function that we will try to produce, because this is degenerate. So the problem is ill-defined if the temperature and the frequency axis are not provided together. But for a given set of values of sigma, you can map that to always a given set value of pi with like a link between the frequency scale you have to use in both cases. So let me show you examples of this. For example, in orange here, you have this function S sigma of S omega, and in blue, you have the function sigma of omega. And we will observe the pi components, okay, so the values in Matsubarra frequencies of corresponding to those two functions. And actually, I have a third one here if you want to think about it. But let's only take those two for now. And we will consider those at 3 different temperatures for the blue one and 2 different temperatures for the yellow one. And you can see that on the blue one, the temperature simply changes the spacing at which you sample a given underlying function for this spectrum. And for the orange one, it's the same thing, like changing the temperature just changes the scaling on that function. Now, those are functions expressed as a function of the Matsubarra frequencies itself. And this grid of Matsubarra frequencies depend on temperature. And if you forget about this grid and only look at the amplitude of those components in order, and you have the same number of components in all the cases, what you find is that at a given temperature, those reverse triangle here, which would be beta over S, you will get exactly the same values than if you use another spectrums, S sigma of S omega, at the temperature beta. And that's what I mean when I say, for given grids, the mapping exists 1-to-1, but if you remove the grid, there is still a mapping between the underlying functions, and you can use that to your advantage by just saying, okay, if I know what is the grid on one side, then I can obtain the function agnostically from the grids and just infer what would be the right grid to use in the other space. So this allows to like take the whole problem and make it temperature independent, because now you can work at any temperature and find the spectra at any other temperature. This is the right place to stop and ask if there are questions about this. So now I found out how I can see you. So if you have questions, you can raise your hand and I will see it. It's okay?
Actually, I have a quick question.
Yeah.
I don't understand how it helps you. I mean, you're saying, okay, it's you can do it independently of temperature, so you have to choose a temperature. If you do it independently, you have to choose one. And then, yeah, I don't see how it helps. I see what it does, but how it helps, I don't understand.
So it's good that you don't see how it helps, because I didn't explain it yet.
All right.
So that's the next step. Okay, but basically you can already think of it like this. If I have those inputs, let's say the reverse triangles here, if a user comes with those inputs, you don't know if the user was working at beta or beta over S. Okay, so if I wanted to produce the output on a single frequency grid, I would have to produce 2 different spectra for the same inputs. So now we will need to design a way to set the frequency grid of the output so that the user can find out afterwards what was the right frequency grid, but we will always output the same amplitude for sigma, if this makes sense. So our contribution to this problem was to explain how you can devise a grid which will always work. And it has other advantages than just being able to work at many temperatures then. Because what happens is that a bright way to do that, and this was the contribution of André-Marie and Reza, is to say, okay, let's take a regularly spaced grid. Okay, so we will take integers from 1 to m, and we will devise those omega of m at which we sample the sigma like this. So let's just say regularly spaced, sorry, from 0 to omega max. And what we will say is that we will take omega max to be defined by the second moment, like the width of the spectrum. And this is perfect because, as you can see, those three functions are the same function with different widths. Okay, so they are all normalized because this is a property of the conductivity. You can know the normalization of the conductivity by the first component. And then if you know the width of the function, you kind of know what is the natural frequency grid on which to express the whole function without losing any information. So you won't produce zeros on those flat parts, and you would have a grid that is always the right size. So this has to do with the fact that this second moment, this width of the sigma function is related to the tail of the Matsubara frequency information. And we use a cubic root here because if you do the math, you find out that this sampling of sigma has to be taken with this s cube. There are subtleties about if you consider the function normalized or not normalized. You have to be careful because there is an extra s that slips in here. So yeah, the details are like, we will need to sit and do this properly, but there is a way to make the problem agnostic from temperature and to always get the optimal grid on which to work in real frequency. So this is extra benefit. Now, what we did to test the idea is the following. We said, let's train a neural network at a given temperature without the rescaling. And let's try the neural network at that given temperature. Let's say I trained the neural network at beta equals 20. Then let's try the neural network at beta equals 30, beta equals 10, or a random selection of betas here. And then you can see that when the neural network is trained at 20, it fails dramatically, like the performance decreased dramatically when you use it at another temperature, just because it was not trained to do that work. But if we always rescale the spectra in the way that all the spectra which you have in your training set give you the Matsubara information always like on a given scale, then you can say, okay, the performance at a given temperature is good, and if you validate at another temperature, you get a lesser loss in performance, like you increase the performance on other temperature. And then the reason why it's not like good at all the temperatures, equally good at all the temperatures, is that the data set that you generated had a given complexity on the frequency grid that you were using. And this complexity of the data set maps to a complexity of inputs that you are trained to treat. And you would have to generate like all possible functions on this frequency grid to have a data set that would be representative of any possible input that you can get. And the problems becomes one then of generating the right data to train at all temperatures simultaneously. And one way you can work around this is to say, okay, but so let's, instead of generating like very complex data, let's train at various temperatures so that, let me go back here. so that if I generate a single spectrum here, I would get various inputs that have to map to this spectrum. So in one case, I had one, so the problem I was trying to solve is that given a single output, I don't want to have two different targets because then the neural network can't be trained properly. But if the problem is reversed and instead of having a single output, I have many inputs, sorry, a single input, I have many inputs that maps to the same output, which is the function on the natural scale, then I can train the neural network to always produce the right spectrum. And you can see this here, because if you train on a collection of temperatures with the rescaling, then you get almost equally good performance as when you were training on a single temperature, but you get it across all of those temperatures. Because implicitly, you have many, many complexities of input and output for the same family of spectra. Okay, so this is the conclusion of the talk. Quantum materials are important for future technologies. We do that computations with quantum Monte-Carlo technique in imaginary time. Returning from imaginary time is ill-conditioned and it's very hard to do. It can be done with neural networks to some extent. And if you rescale the targets properly, you're allowed to generalize better. And this is our contribution to that work. So obviously, starting from there, ways of generating data would be an interesting avenue forward. Different architectures for the neural network would be an interesting avenue forward. As I said, we have ideas about like using the frequency as an input to the neural network to have more general functions in the end. And yeah, so if you want to talk about this and if you're interested to work on this, I would be happy to have like a private meeting with you just to discuss the plans that I had for the future, and that will probably not concretize because I'm finishing my postdoc very, very quickly. So thank you very much.
Yeah, thank you very much, Simon, again. So does anybody have a question before we wrap this meeting up? Nope, I see no questions. So again, thank you. And I think, yeah, that's the end of this. Oh, no, there was no question. All right. So yeah, thank you, everyone. We'll see you next week. Oh, yeah, sure.
Yeah. So thanks for the talk. Very interesting. So what kind of problem? So at some point you can like tune a bit your output. So in the first example, it's the sum, and so you have x1 to x5 gives you a y, and then you can generate y1 to y5 by changing something in your initial formulation, and that's what essentially you do. But is this like generally like what kinds of problem let you do this, and what kinds of, do you know of any kinds of problem that could not let you generate a lot of samples for your output, for example?
Okay, so yeah, this is a good question. So in general, in inverse problems, this is a huge class of problems. For example, tomography is a kind of inverse problem, trying to find the structure in an MRI of what give you the image is an inverse problem, things like this. Inverse problems in general has this property that the forward problem is relatively easy and stable compared to the inverse problem. So you can generate almost an infinite amount of data for those problems in most of the case. So the limitation that you will probably have is that when you will generate those data, you have to be very careful about like the precision of the integration for the forward problem. Because if you get a bias, for example, when you're doing the integral 10,000 times, if you always make the same mistake because you used an integral grid that was not the right one, or you use some parameters for your integration which were not precise enough, then if you work with neural networks to do the inverse problem, you will learn this bias. You will learn to always do this error, and then you will mess up the algorithm.
Okay.
So I don't know if this answers.
Yes.
That was it? Okay.
Mm-hmm.
Because maybe your question could also be interpreted in like this particular problem. I has this epsilon value that I could change, but this was just to change the problem. And this is not something I can do for the analytic continuation.
Okay, so we'll see you next week for the next student seminar.
Okay, thank you very much. And sorry,
Bye, everyone.
I think I went way over time, right? Oh no, that's